So I welcome you all for the pre-runner gate class. So the previous class we have discussed the active filters, and then we have solved the gate problems, gate question problem. So in this class we are going to discuss analog to digital converter and digital to analog converter. So in general we are all know that so most of the real world, the physical quantities are okay. So it should be in analog form. Okay. So analog form that is for example voltage, current, temperature, pressure, and time, etc. So here this analog parameters are that is it is very difficult to process and store and transmit. Okay, so here it introduced the more error. Okay, so because of we are going for the digital data, so we should convert the analog data as converted should be digital. Okay, so here the digital data we are using the digital data, we are processing the digital data and transmit the digital data and storage the digital data is very convenient, and also the accuracy is very high. Okay. So here we go for the digital data. So and also we are reducing the noise. So in all the communication, so we use the digital data. Okay. So here in general, in conversion we use the analog to digital converter, digital to analog converter. So this is the like a block diagram of the A to D and D to A converter. So any applications we are using this conversion. Okay. So first in sensor transducer we have the physical quantities are for example voltage or current considered. So this should be in analog form. So this analog signal is given to the anti-aliasing filter. Okay, anti-aliasing filter. So this aliasing filter can eliminate the error signal. So error signal in that analog signal. So that signal is given to the sample hold cycle. So here we should know that the sampling theorem, that is the input signal frequency, it should be that is 2fh, right? So the sampling frequency should be greater than or equal to 2 maximum analog signal frequency. So here the analog signals are converted into discrete form, right? So using that sample hold cycle, sample hold cycle. So here this discrete form, this is again analog signals which is converted into digital form. So using that analog to digital converter, right? So here we are getting the digital signal. So that signal is going to be processed, right? So the processing is nothing but depending upon our application, right? So whatever the applications, based on that we are going to process the signal. So after that processing the digital signal, which is given into and receiver side, we have the digital to analog converter. So here the digital data is converted into analog. So that signal is given to one filter, that is smoothing filter. So here this we are getting the analog signal. So that analog signal, it should be transmitted original signal without error, without any noise, right? So this is the general that is in any communication, right? So we convert analog into digital in transmitter side, digital into analog in receiver side, right? So this is the basic thing. So we should know that. Then we go for the converter, right? So analog to digital converter. So where we use the analog to digital converter, right? So in many application, okay. So in many application we are using the analog to digital converter. For example, consider the computer. So here we using the music and that is video synthesis, then modulation, right? In communication, pulse code modulation, then data transmission, then digital multimeter. So here then digital signal processor, right? So wherever we use the digital signal, we use the converter, right? So here for all the applications, right? So many applications we are using the this converter. So first we'll see the basic digital to analog converter technique. So this is the symbol block diagram of the digital to analog converter. So here input is the digital data. So our output is the analog data, right? So are considered n-bit binary word. So consider the n-bit binary word is D1, D2, up to we have Dn. Then output voltage we are denoted V0, right? So the binary word is we are represent from LSB to MSB, the word represent the D. So this is analog form as, right? So this input is given to digital to analog converter. So the analog form we are denoted V0 with the reference voltage is VR, right? So this is the basic block diagram, right? Schematic diagram of the digital to analog converter. So here we are going to give the input signal to the this converter, D2A converter, which is combined with the reference voltage. Okay, the reference voltage which produce the analog output signal. Okay, so the analog output signal we are denoted V0. Okay, right? So the analog output voltage, it may be that is any other form, that is any physical quantities. Consider here voltage, voltages or current. Okay. So how we represent this that is digital to analog converter mathematically. So how we represent this conversion is mathematically. So here the analog output voltage V0 equal to K into VFS. We have the binary data as D1, D2 up to we have Dn, right? So here the word is D1 to Dn, right? So D1 2 power minus 1 plus D2 2 power minus 2 up to we have Dn 2 power minus n. Okay, so here our V0 is the output voltage. It should be analog form. So here K is the scaling factor. Then VFS is, so VFS is the full scale output voltage. Then D1 to Dn is the binary word. It is from that is MSB to LSB. Okay, MSB to LSB. So this is the general block diagram how we convert the binary that is digital data is converted into analog. Okay, this is a simple technique. So anyway, here the next we are going to discuss we have the various types of the digital to analog converter, right? So we'll see one by one. So the first one is the binary weighted register type D2A converter. Okay, binary weighted register type D2A converter. Then we have R2 to R ladder type D2A converter. Then we have voltage mode and current mode R2 to R ladder type D2A converter. So we'll discuss one by one, right? So the first one is the binary weighted register type D2A converter. So this is the circuit diagram for this D2A converter. We have in this circuit diagram, we have op-amp with, we have the weighted register network, right? That is binary weighted register network. So here, all of you listen here. So here is we have the binary weights are, that is 2 power 1, 2 power 2, 2 power 3, we have 2 power n. So you are considered the binary words are from MSB to LSB, that is D1 to Dn, right? D1 to Dn, that is D1, D2, D3, Dn. So this binary weighted register network is which is connected to the inverting terminal of this operational amplifier, right? Then here the non-inverting terminal should be grounded. Okay, so here this binary weighted register type register network is, that is here we have in this binary word which is connected into one switch, right? So we use the different types of switch. So one is the that is the single pole double throw switch. Then another one is the we have the TTL logic switch. But in this converter we use the single pole double throw switch. Okay. So here in single pole double throw switch, that is here as input should be, in that we using this switch means we should give the input should be the input should be the negative voltage, right? So here we are given the negative reference voltage. Okay, negative reference voltage. So depending upon the binary word. So here what is the binary word? So here the binary word in general we are represent the zeros and one, right? Binary inputs are zeros and one. So it is 0 means, so here the switch is connected to ground, right? So it is 1 means which is connected to the reference voltage VR, minus VR, okay, minus VR. So now we are going to analyze we are going to give the binary weighted input. What is the output voltage in this circuit, right? So here, what is the non-inverting terminal voltage? The non-inverting terminal is which is connected to ground, okay, connected to ground. Output is fed back to here inverting terminal through the feedback resistance. So all that is everyone should know that the virtual ground concept, right? So here you know that the difference voltage in operational amplifier, consider ideal op-amp, right? So here the difference voltage should be what? So the difference voltage is 0, right? That is the difference voltage, that is non-inverting terminal voltage minus of the inverting terminal voltage should be 0. That is current flows through the terminal should be 0. Anyway, here the non-inverting terminal should be grounded here, right? So whatever that in non-inverting terminal voltage, here what voltage is that voltage should be present in the inverting terminal, right? So here it means this node is, right? This node is, it is act as the terminal as well as the virtual ground. Okay, so it is act as terminal as well as the virtual ground. So here we have V0, right? We have V0. So here current flows through the that is we have resistance are there, right? So V naught is there, resistance are there. So current should be there. So current flows with this feedback resistance, we are denoted I naught. Okay, so here I naught is the considered, it is the entering current, right? So here this entering current I naught, right? So this I naught is, right, which is flows through this binary weighted resistor. That is I naught equal to, that is, so this I naught is, which is divided into, we have sum of current. So the currents are I1, I2, I3, we have up to IN. Okay, IN, right? So now we are, let us, we are applying the Kirchhoff's voltage law, sorry, Kirchhoff's current law at the node A, right? Kirchhoff's current law at the node A. That is sum of these currents, right? So N current, that is I1, I2 up to IN. So this sum of this current, it should be equal to what? It is the 0, right? It is 0. So here, I'll have to listen now. So just write the current equation, right? So here we have VA is there, right? Sum of these currents are, it should be equal to 0, right? That is current flows through the inverting terminal should be 0. So current at this terminal should be 0. Okay, understand, pa? So it should be 0. So just write the current equation, right? We apply the Kirchhoff's current law at the node, this node, right? So here consider the node as A. So here apply the Kirchhoff's current law. So here is VA, just write the equation. So what is VA here? Here is VA, we are denoted the voltage is VA, right? So VA minus V naught, VA minus V naught divided by the feedback resistance RF. Okay, then we have VA, that is the switch is this position, that is the right position, right? So right position means which is connected here, right? So here switch is right position means it is the binary input is 1, right? Which is connected to the reference voltage minus VR. Okay, so VA minus V naught divided by the feedback resistance. The next one is the VA minus of, we have the reference voltage is negative, right? So minus of minus VR. Okay, minus VR divided by what is the binary weighted resistance? The first resistance is 2 power 1 R, right? Then here, what is the binary word? So here it is the D1. So similarly, we can write it the second one, third one up to nth one, right? So VA minus of minus V reference, right? Minus of minus V reference divided by 2 power 2 into R into D2, right? Plus up to we have N, right? That is binary weights are 2 power N is there, right? So here 2 power N. So VA minus of the last one is the last current is the IN, right? So VA minus of minus VR divided by 2NR. Okay, 2NR. So here the binary word is DN. So it should be equal to 0, right? It should be equal to 0. That is, sum of these currents should be equal to 0. Current flow entering into this terminal should be 0. Understand, pa? So here it is 0, right? So now we are going to simplify this equation. So here I consider here the V naught term should be right side, right? So the reference voltage term consider the left side. So what we'll get? So here is V naught divided by RF feedback resistance is there. So that term only I consider the right side, right? So V naught divided by RF. So what is the remaining term? So here is, you should know that what is VA voltage at the node A? What is the voltage at the node A? So here this is inverting terminal voltage, right? So non-inverting terminal is grounded. So the same voltage should be present here. So VA also 0. So in this current equation, you substitute VA equal to 0. Okay, VA equal to 0. So what we'll get? So here is VA 0 means my plus VR divided by 2 power 1 R D1 plus here is VR divided by 2 power 2 R D2 plus up to we have plus VR divided by 2 power n R into Dn, right? So this is equal to V naught divided by R. So from that, what is the analog output voltage? So analog output voltage V naught equal to, we have feedback resistances RF. These are current terms, right? So here the sum of this current, it should be equal to what? It should be equal to I naught. So that is I1 plus I2 plus I3 plus IN, it should be equal to I naught. That is entering current is I naught, leaving currents are I1 to IN. Clear? So here it should be I naught, right? So anyway, so these terms are, the sum of these currents are, we are present I naught. So I naught into we have the feedback resistance, right? So here our converter output is listen. So we are given the inputs are binary word. So the binary words are n binary word, that is D1 to Dn we are given. So what is the analog output voltage? So analog output voltage is I naught into RF, right? Okay, I naught into RF. So where I naught is sum of the N current, I1, I2 up to we have IN. Understand? So here, just write that the I naught. So I naught is from this current equation. What is I naught, right? So I naught is, we are simply write this. That is, we are consider only the current term, V divided by R is here. So remaining terms are, that is binary weighted, weighted input, right? So 2 power minus 1 D1. That is, we have D1, it should be the denominator 2 power 1 is there, right? It should be numerator means 2 power minus 1, right? Right. So anyway, binary weights are 2 power minus 1 to 2 power minus n. Here, the binary words are T1 to Dn. Okay. So here the output voltage V naught is, we have derived I naught into RF, right? I naught into RF. So what is V naught? So V naught is, see, V naught, what is V naught? V naught equal to I naught is, what is I naught? VR divided by R. Just we substitute, right? VR divided by R, the remain this term. Okay. Then we have feedback resistance is there. So VR divided by R into V also we have feedback resistance. So here we consider, that is we just compare the first two equation, right? First two equation. So anyway, here it just correlate, right? So the reference voltage. So what is the the feedback resistance, right? So the feedback, first one is the feedback resistance. So RF equal to R, right? Here compare first and second equations. What is RF? RF equal to R. Then what is K? That is K equal to, see, so K equal to 1. Then what is VFS? Full scale output voltages. Full scale voltage is the reference voltage, right? Full scale voltage is the reference voltage. So here in that converter, binary weighted register converter, so our input is the digital form, our output is the analog voltage. We just draw the transfer characteristics of the analog, digital to analog converter, right? So our input is digital input code. Our output is the analog output. So here we are consider, for example, you consider the inputs are 3-bit. Binary words are 3-bit, right? So from 0030 to we have maximum is 111. So what is the binary equivalent analog, right? So the analog voltages. So here it is 0 to 7 VR by 8, right? So here is, it should be 1 by 8 VR, 2 by 8 VR, 3 VR by 8, 4 VR by 8, up to we have 7 VR by 8, right? Then maximum is, we have the reference voltage. The next one is 8 VR by 8, it is reference voltage VR. So anyway, the transfer characteristics of the 3-bit digital to analog converter is, it's like a staircase. Okay, like a staircase. Then here we should know note that, so here is, this input is, that is the reference voltages, right? So the reference voltages which is connected to the inverting mode, right? Okay, inverting mode. So the output voltage is, see, here, all of you listen. So here, the reference voltage is connected to inverting, and also we are connect the reference voltages, it is non-inverting terminal also, right? So here, so that type of converter is the non-inverting binary weighted register type D2A converter. This is the inverting type. Anyway, so here depending upon the switch position, that is, it is the right position means it is connected to minus VR, right? Minus VR. So all the binary words are connected to this, right? So here binary words are converted into analog form. That is, digital is converted into analog form. So here the switch position is left position means it is the which is connected to ground. Okay, which is connected to ground. So just you note down this. So here the input is also connected to the non-inverting mode. Anyway, so here depending upon the type of switch, right? So the reference voltage is either positive or negative. So here we consider the single pole double throw switch. Okay, so here we use the single pole double throw switch. So using this type of switch, here we use the reference voltage is negative. So reference voltage is negative means which is connected to inverting terminal, right? So the output voltage should be positive. Okay, so we use the type of switches transistor logic, right? Transistor logic, that type of switch means the reference voltage should be positive. So the reference voltage is positive means the output voltage is negative, right? So here you should note on this the points. Okay, then here, what is the advantage? That is, what is the first disadvantage of this? The this binary weighted register R2 to our digital to analog converter, right? So what is the disadvantage? So here is the binary weights are 2 power 1 2. See, 2 power 1 to 2 power n. So the resistance are fixed resistance, right? The binary words are 2 power 1 to 2 power n. So here is 2, here is 4r, right? 4, here is 8. So depending upon the 2 power, they are getting the resistance values are double, right? So anyway, so the drawback of this converter is here is one end, here is one end is here the small resistor values, right? So another end is the resistor value is very large, right? So here we use the wide range of resistor. Okay, Mama. So here one end is it is the small resistor. So another end is we should use the wide range of resistor. So here that is we are all know that the large resistor, large values of resistor, right? So it is very difficult to fabricate. It is impractical, right? So impractical to fabricate the large values of resistor in integrated circuit. And also here we use the large resistor means the voltage drop, right? So voltage drop across the large resistor is due to bias current. Okay, due to bias current. So here this will affect the accuracy of the converter, right? So here one end is we have small resistor. So small resistor is affect with the loading effect, right? So loading effect. So this is the main disadvantage of this binary weighted resistor type D2A converter. So you avoid that. So avoid this problem. So we go for the next type, that is the R2 to R ladder type D2A converter. So here we use the fixed resistance, right? Okay, so here is depending upon the binary word, the resistance values are increased. That is 2 power 1, it is 2R. So 2 power 2R means it is 4R. 2 power 3R means it is 8R, right? So here we use, in that type, we use the fixed resistor, only R and 2R. Okay, so this is the circuit diagram of the R2 to R ladder type digital to analog converter. So here we have op-amp with this R2 to R ladder circuit, right? So here we use the binary words are 3-bit. For example, we consider 3-bit. So what will happen, right? So we are given the 3-bit binary word. So this is the digital data. So what is the analog output voltage? Okay, so we are going to now analyze this circuits. Anyway, so we have op-amp, right? So here is we have R2 to R ladder network is there. So this switch connection is similar to the first one. That is it is the right position means it is connected to minus VR. So here also we use the single pole double throw switch. It is the left position means it is the connected to ground. So here we consider the binary words are 1, that is 1 0, right? 1 0 0 1 0 0. Okay. So here input is connected to the inverting terminal. So here the non-inverting terminal is grounded. Output is fed back to the inverting terminal through we have feedback resistances. We are considered 2R. Okay. So here R2 to R we have R input resistance R 2R here, right? R 2R. Here R 2R. Here we have 2R. Feedback resistance also 2R. Okay. So now we are given the inputs are, we are going to give the inputs are only 3-bit. We are considered 100, right? So this is the digital data. So what is the analog output voltage, right? So we are going to analyze. So see, so here the digital input is 1. 1 means which is connected to the reference voltage, right? So it is the right position. So here it is connected to the reference voltage minus VR. It is 0 means which is connected to the ground, right? So it is 0. So it is connected to ground. It is 0. It is also connected to 0. So only this switch is connected to the reference voltage. These two switches are connected to ground, right? So just redraw this whole circuit, right? Okay. So which is that circuit is considered as equivalent circuit. So anyway, just redraw the circuit, right? So here op-amp we have resistance. You just draw as it is, right? Then here this portion is this R2 to R ladder portion is here. This switch is only connected to the reference voltage, right? So here 2R is which is connected to minus VR. Then remaining here we have R to R. So this 2R is connected to ground, right? Then we have R is there. Then this 2R connected to ground. We have 1 2R, right? So this is the equivalent circuit of the R2 to R ladder circuit, right? So now we are going to simplify that, right? This that is we have to simplify. That is we have to find the resistance value for this circuit. So anyway, so just analyze that. Here is the 2R. 2R to R is these two resistance are connected in parallel, right? This is connected with this resistance are connected with series, right? This are connected with this resistance are parallel, right? These are connected with series. So anyway, so here is just analyze the cycle. You just find the resistance value, right? Find the resistance value. This R to R, sorry, 2R to R is parallel, right? Parallel means we are getting R. Then this R is connected with this resistance is series. So R plus R, it is 2R, right? Then 2R is, that 2R value is, this 2R connected with parallel. So 2R parallel of 2R, it is R, right? We know that. Anyway, it is R, then that R is connected with series, R plus R, right? R plus R is connected with series. So here 2R we are getting. So we have 2R, 2R. Here input resistance 1R is there. Then another 2R is connected to the reference voltage. Okay. So we just simplify the cycle, right? So the circuit test, we'll get the circuit test in the C node. So this is the C node, right? So here this 2R is connected to the reference voltage. What is this resistance value? 2R, right? So we 2R is minus, that is C. We have 2R is connected with the reference voltage. The equivalent resistance value is 2R. This is the input resistance value, right? So the input resistance value is also connected to the ground. This is a virtual ground, right? So here the non-inverting is connected ground. So it is, this is act as terminal as well as the virtual ground. So here consider here virtual ground. So it should be grounded, right? It should be ground. So now we find the voltage across the terminal C, right? Voltage across this terminal C. So these two resistance are connected in parallel. So we find the resistance value. So the resistance values are 2 by 3 R, right? 2 by 3 R. Then we have 2 R is there. So these two are connected in what? Parallel, right? So here what is VC? So VC is minus VR 2R by 3. So here we are finding this node voltage, right? So how we find this node voltage? So voltage at that node, this node, right? So we are considered this resistance. So how we find this VC? So VC is minus VR 2 by 3 R divided by 2R plus 2 by 3 R. Okay. So you simplify that, right? So you simplify that, we'll get the voltage at that node C is, that is VC equal to minus VR divided by 4. Okay, minus VR divided by 4. So now the final cycle diagram is, that is the voltage at the node is, see, we are calculating the voltage at the node, right? So this is minus VR by 4, we are derived, right? So minus VR divided by 4. This is the input of the inverting terminal. We have input resistance is there, then feedback resistance also there to R. Just draw the cycle, right? So this is the input minus VR by 4. So this input is given to inverting terminal. So what is the output voltage, right? So you know that inverting, this is the inverting amplifier. Input is given to inverting amplifier. So what is the output voltage? You should know the gain of the inverting amplifier. The inverting amplifier gain is minus R by R. Everyone know that. So anyway, just apply that concept, right? So V naught equal to minus 2R divided by R. So the input voltage is minus VR divided by 4. Okay. So simplify that, we'll get the VR divided by 2. So the output voltage is VR divided by 2. So the reference voltage is the full scale voltage. So anyway, it is the full scale voltage. So here, what is V naught? VFS divided by 2. So the output voltage is VFS divided by 2. So here the binary words are, actually here the given, the inputs are binary. So what is the output voltage? So here binary words are 100, right? It is 100. Our output is what is the output? Analog output voltage, that is VFS divided by 2. Okay, VFS divided by 2. So here is in that binary weighted register, we have the problem is that it is one end we have small register, another end is we have the large register. Okay, so voltage drop is in that large resistor, it is very large due to bias current, right? So small resistor, this will affect with the loading effect. So that we go for the fixed resistance LADAR D2A converter. So here also we can have the one disadvantage. So what is the disadvantage of this R2 2R R2 2R LADAR type, right? So current, see, both type, binary weighted resistor type and R2 2R LADAR type D2A converter. So current flowing through the resistor, right? Current flowing through the resistor changes as the input data. Okay. current flowing through the resistor changes as the input data. Depending upon the input data, current flowing through the resistor is changed, right? So this is the main disadvantage of this two type, that is weighted resistor, binary weighted resistor type D2A converter, and then R2 or ladder type D2A converter. And also here, the disadvantage is it has more power dissipation. Okay, so more power dissipation causes heating, and also it creates the non-linearity. So non-linearity is the very big problem, that is we cannot get the digital equivalent to analog, right? So it is very serious problem. So we avoid that, right? We are completely avoid that. We go for the inverted R2 to R ladder type digital to analog converter. Okay, so next we will see the inverted R2 to R ladder type D2A converter, right? So first one is the that is, it is a 3-bit inverted R2 to R ladder type digital to analog converter. So here we have two types. So the first one is the current mode, second one is the voltage mode. Okay, so first we will discuss the current mode. Current mode, inverted R2 to R ladder type digital to analog converter. So here we have op-amp with R2 to R ladder type circuit, right? Ladder type circuit. So here, see, here, what is the disadvantage of the previous one? So here is, what is the disadvantage? So current flowing through the resistor is changes means this will affect, that is changes is depending upon the input data, right? So here the serious problem is non-linearity problem, right? So avoid that, we go for this one. Okay, so here is, so all of you listen, here is, so here the switch position is either right position or left position. See, so the network is R2 to R, this ladder type network is which is connected to the inverting terminal. The non-inverting terminal is, it should be grounded, right? The switch is either right position, which is connected to this node, right? Anyway, input node, right? Anyway, it is input node, and also we know that it is act as the, this is ground means this is act as the virtual ground, right? So here you can say that it is right position means which is connected to, it is ground, right? Virtual ground. It is left position means it is connected to the ground, right? It is connected to ground. So here current flows through the resistor, right? Current flows through the resistor changes is does not depends upon the input data. So what is the input data? Binary data. So binary data is connected, that is it is either 1 or 0. Current flows through this resistance are constant. Okay, it is constant. Okay, so that we go for this inverted R2 to R ladder type. Understand pa? So anyway, okay. So here, so that is the circuit, that is current flows through the all the resistance are constant. So here, listen. So here the reference voltage is minus VR. Current flows through the resistance are constant means here minus VR. So the currents are constant, right? So here the voltages at that node also equally divided. So here minus VR. So here this node we have minus VR. Okay. So here this node we have the reference voltages minus VR divided by 2. So this node, this is divided into 2. So here the node voltage is minus VR by 4. Okay, minus VR by 4. Minus VR by. So here the voltages at that node also equally divided. So currents are, now we just write the current equation, right? So I1, I2, I3 currents. So these currents are constant, right? These currents are constant. So anyway, so I1 equal to minus VR divided by 2R, I2 equal to minus VR divided by 2 divided by 2R. So I3 equal to minus VR divided by 4 divided by 2R. Okay, so what is V0? We know that I0 into RF, I0 into RF. So RF, this is RF. So what is I0? I0 is the sum of this current. So what is the sum of this current? I1, I2, I3, right? I1, I2, I3. Here is, we just substitute that I1, right? I1, I2, I3. That is minus VR. We have feedback resistance. We have divided by R. Okay, we have divided by R is there, right? Divided by R. So here the datas are, binary datas are D1 2 power minus 1 plus D2 2 power minus 2 plus D3 2 power minus 3. Okay, 2 power minus 3. Okay, so here input changes does not affect the current flows through the resistance. Okay, so that we use this inverted R2 to R. Input changes either 1 or 0, right? The inputs are either 1 or 0. Current flows through the resistance should be constant, right? So here we just redraw the cycle, right? We just redraw the cycle. So this here we consider the previous actually given circuit is, and here is given circuit is, here voltages we are considered, right? So each node the voltages are equally divided. Similarly, we have considered current. So here I consider the currents are 2 microamps, right? So at that node we have 2 microamps. So what is this node current, right? So this 2 microamps current is equally divided, right? So current flows through two resistance are equal. So any switch positions are either right or left, right? It should be constant. So currents are equally divided. So the 2 microamps are equally divided here, right? 1 microamp, 1 microamp. So here we have 1 microamp. So this 1 microamp is equally divided here, right? 0.5 microamp. Here also 0.5 microamp. So here 0.5 we have. So this is divided into 0.25, 0.25 microamp. Okay. 0.25, 0.25 microamp. Okay, Appa, right? Okay. So just write that the current term, right? So in the node A, we have 1 microamp. Node A, in this here we have 1 microamp, here we have 1 microamp. So 1 plus 1 it is 2. Just write the values, right? So at node B we have 0.5, 0.5. So this node we have 1. Then here at this node 0.25, 0.25 we have this node is 0.5. Okay. So this is the current mode. This is the current mode. Right, current mode inverted R2 to R, D to A converter. So the next one is the voltage mode. So inverted R2 to R, ladder type digital to analog converter. So this is the voltage mode. So this circuit is, right? So op-amp with we have the R2 to R. So this R2 to R ladder circuit is which is connected with the reference voltages, right? So here we use the reference voltages high and low reference voltage, right? So high, like consider it is a threshold voltage, right? Maximum voltage, here is the minimum voltage. It is not 0, anyway it is minimum voltage, right? So here the switch position is, it is the right position means which is connected to the voltage source is high, right? VH. Then switch position is left position means which is connected to the, that is, yeah. So this is, which is connected to the binary word, right? See here, left or right, switch position is this. See here, left or right, which is connected to both the voltage source, that is VH and VL. Okay. Then here we have to give the binary words are n binary words, right? So binary words B1, B2, B3, Pn. So here we use the voltage, right? Voltage sources, high and low voltage sources. So now we analyze we are given the binary word, right? That is the digital data. What is the output voltage of this circuit, right? So here we have voltage sources, 2 voltage sources are there. Okay. Now we find the voltage at that node, this node. This node we are going to calculate, right? So consider the node is S. So what is the voltage at the node S? So I represent Vs. So what is Vs, right? So Vs is, it is minimum voltage is, V0 minimum is only low voltage. It is not 0, right? Maximum voltage should be, what is the maximum voltage is? VH minus of, right? VH minus of the binary word, right? That binary word maximum n bit we have. So 2 power minus n, the difference voltage, VH minus of VL, right? VH minus of VL. Okay, VH minus of VL. So here we are just represent the node voltage is Vs, right? So the Vs is given to the non-inverting terminal. What is the output voltage? So here Vs is given to non-inverting terminal means it is the non-inverting amplifier. So you know that the gain of the non-inverting amplifier is 1 plus R by R. Here RF is R2, input resistance is R1. So 1 plus R2 divided by R1 into the non-inverting terminal voltage, that is Vs. Okay, Vs. So this is the voltage mode, right? Voltage mode. So here the switch position is, the switch position is does not depends with the input values changes, right? Okay. So here also we can say that current flow, that is the current flows through the resistance are constant, right? Current flows through the resistance does not depends upon the binary values. Okay, binary values. So anyway, so here V naught equal to, what is V naught? 1 plus R2 divided by R1 into the Vs. Okay, R2 divided by R1 into Vs. So here up to that we have discussed different types of the digital to analog converter. First we have discussed what? Binary weighted register type, R2 to R, R2 to R, right? I just revised that. So binary weighted register type, R2 to R, okay, R2 to R. So here we have one main disadvantage is that is binary weights are, it is linearly increased, 2 power 1, 2 power 2, 2 power 3, up to we have 2 power n. So what is the main disadvantage? So here one end we have small value, another end we have large value. So it is impossible, that is impractical to fabricate the in IC, right? In IC, one end is small value, one end is large value, right? Okay, so and also that is, we know that large resistance are due to bias current, here voltage drop is high, right? So this will also affect the accuracy. Small resistance means it will affect the loading effect, right? So loading effect may occur. So this is the main drawback of the binary weighted register type D2A converter. So avoid that, we go for the R2 to R. Here is we are using the fixed resistance, right? Only R and 2R. Okay, R to R. Only resistance values R and 2R. Okay, but here also we have some disadvantage. What is the disadvantage? Here is depending, that is current flows to the resistance changes is based on that input. Okay, based on that input, that is in position is either right side or left side, right? Which right side means which is connected to reference, left side means which is connected to ground, right? So current flows through the resistances changes with the input data, right? Changes with input data. So here that is what is the, it is changes with input data. So the so that here is some non-linearity problem will occur, right? That is we cannot get the digital equivalent analog output. It is a very serious problem, right? So that we go for the next type, last type, that is inverter R2 to R ladder type digital to analog converter. So we have in inverter R2 to R ladder type, current mode is there, voltage mode is there, right? So in current mode here is, it does not, that is current flows through the resistance are does not depends the what switch position, right? That is the binary word, either it is 1 or 0 which is connected to the ground, right? This is also virtual ground. Okay, so current flows through the resistance should be constant. Okay, current flows through the resistance should be constant. This is not changes with respect to the binary word. Okay, so here we'll get the, that is the converter which convert the accurate digital equivalent analog. That is the accuracy. We are improving the accuracy of the converter. Okay. Similarly, here next one we have the voltage mode. So here we use the high and low voltage sources, right? Low voltage sources. Here also the switch position does not depends upon this binary word, either right or left, which is connected to the voltage source. Okay, voltage source. So right. So here also that is current does not change with the binary data, right? In voltage mode also. So here also we are improving the accuracy of the digital to analog converter. Okay, analog converter. The next one is we have the basic A to D converter. So before that we are discussed the digital to analog converter, right? So the next topic is A to D converter. Okay, analog to digital converter. So in analog to, it is the reverse of D to A converter, right? Just opposite that of D to A converter. So input is the analog voltage, our output is the digital data, that is binary word. So how we can write how we can write the digital input analog, digital output analog input, right? So see here the binary words are general, we are represent n bit d1 to dn. Okay, so d1 to dn we are represent the function value as d. So d equal to d1 2 power minus 1, d2 2 power minus 2, up to we have dn 2 power minus n. So here d1 is the MSB bit, dn is the LSB bit. In analog to digital converter, we use the two control lines, right? Okay, two control lines. That control lines are start control line, then end of conversion control line, right? So the start control line, what is the use of that? So here we are given the input, right? So the input, it means that control lines in the start, right? So here input to tell the analog to digital converter when the conversion is start, right? When the conversion is start. So the conversion is starts means the start control lines are enabled, right? So end of conversion. So after we are convert the analog to digital data, right? Analog is converted into digital data. So the end of conversion. So here this control line is enabled, right? So which tells the conversion is complete. This start control lines which tells the start the conversion. This is which announce the conversion is complete, right? So we have here is two control lines, that start control line, then end of control line. Sorry, end of control line, right? That is end of conversion. Control line is conversion. Okay, so where we use this analog to digital converter. Okay, analog to digital converter. So all the microprocessor interfacing, we use the analog to digital converter, right? So in this op-amp circuit, we have analog to digital converter. We have two type. So first one is the direct type analog to digital converter. Then second one is the integrating type analog to digital converter. We have two types of A to D converter, right? So first type is direct type analog to digital. We'll see the first one, right? And direct type analog to digital converter. So direct type means we are going to give the analog signal, right? Analog signal. So you should get the digital. So analog signal, we compare the analog signal with the internally generated equivalent signal. Direct type is we just compare the analog signal with internally generated equivalent signal, right? So that type of analog to digital converter is direct type analog to digital converter. So in that we have two types is there, right? So the first one is the flash type A to D converter. It is also called as the parallel comparator. It is called as fastest A to D converter, right? Then second type is the successive approximation type analog to digital converter. Okay. Then next one is the integrating type analog to digital converter. So integrating means that is integrating. First, the analog data is the function of time or frequency, any other physical quantity, right? Right. So first that is integrating type is it perform the conversion in indirect manner, right? It is the direct one. It is the indirect manner. First, changing the analog signal into linear function of time. First, the input signal, analog signal is changed into linear function of time or frequency. After that, we are converted into digital form, right? So here we have the two types of integrating type A to D converter. So the first one is the single slope A to D converter. Second one is the dual slope A to D converter, right? Okay. So in direct type, we have the two converter, flash type A to D converter, successive approximation type A to D converter. In integrating type, we have the two types, single slope A to D converter, dual slope A to D converter, right? So you'll see one by one in the next class, right? Okay. So here we revise the theory concept, right? So the next class we'll see the remaining thing, that is what is the different types of the A to D converter, direct type